Good morning, everyone. Thank you to the session chairs and audiences for joining this session. I'm Ibn Qasr, and today I'll be presenting attention-based imputation of missing values in electronic health records tabular data. This is the overview of the presentation, where I'll be first going through the introduction of the topic and the motivation behind the problems and the methods that we have performed to deal with the problems, and the results, summary, and conclusion of the work. To begin with, this work is mainly based on electronic health records data and medical centers archive patients' data in electronic health record database as structured in tabular data with heterogeneous feature space as shown in this picture. And statisticians and data scientists analyze this medical data to solve unsolved research questions like predicting clinical outcomes, to prognosticate or discover normal clinical values, or suggest therapies for treatment, and many more unsolved problems. However, collecting these EHR data is complex due to few cases. For example, patient visits can happen at irregular intervals, and also not all measurements are taken for each time a patient visits their medical centers. And also there might be a broken sensor or loss of data due to technical or human error. In all these scenarios generates missing clinical samples or missing clinical variables. And due to this, there are some pitfalls of missing values in electronic health record data. For example, first and foremost, the important thing is that machine learning models are inoperable when we have missing values. And if we want to drop the missing values due to the high missing rates, this might be the case that we are dropping a potential valuable predictor of the classification problem, and which might result in some extreme cases misdiagnosis. And another example could be that if we have a data set which is like this garbage in, and if we do not curate the data or clean the data and train a machine learning model, and the output we'll get will be the garbage out. And however, we don't want this suboptimal accuracy or poor generalizability of data-driven predictive models. So therefore, again, as machine learning models are inoperable on tabular data with missing values, it is crucial to do data imputation on electronic health record data domain. It is most commonly used that practitioners or data scientists and statisticians uses mice-based imputation to deal with the problem. And mice-based imputation is basically linear regressors with multiple chained equations. And later on, this mice-based imputation is replaced by a decision tree-based regressors, which is known as misforest. Even though these two methods are very well accepted among the practitioners due to their easy accessibility and usability, however, there are some limitations, and those limitations are very complex, and we need to deal with that for EHR domain, because Mera et al. Says that mice is computationally expensive on large and complex data set, which is the case for electronic health record data. And this happens due to the nature that mice imputation uses linear regressor in multiple chain equation, which is why if we have a lot of clinical variables, the number of linear equation increases, and which results in expensive computations. And another case is that when you have high missing rate, Liao et al. Argues that misforest overfits on tabular datasets with high missing rates. And in recent advancement with AI, it seems the deep learning model has improved text, image, video, and audio domain drastically. However, tabular data domain, it showed limited success. And if we can check more literature, it shows that deep learning networks are considered at the last unconquered castle and for tabular data, and normal traditional tree-based methods outperforms neural network on tabular data. And there is a strong non-deep competitor in the form of gradient boosting trees of neural network. However, even though we see all these shortcomings of deep learning-based methods when it comes to deep tabular data. There are some promising literature that shows that attention-based methods can outperform traditional deep learning-based methods, which is that non-parametric transformer, feature tokenizer transformer, and Saint transformer. All these methods shows that they shows promising result in compared to gradient boosting trees and other traditional machine learning methods. However, attention-based learning for missing values in tabular data has not been well explored. Therefore, we hypothesized that attending between EHR variables by deep attention-based representation learning would improve missing value estimations over state-of-the-art regression-based models. Now, before we check how we implemented implemented our methods, let's check what was the first attention-based methods that was proposed by Vaswani et al. In 2017. Here is an example that how a regressive capes form. This is a sentence, and how they convert that word embedding to an embedding vector, which is a metric. And in this metric, each row represents a word. And from these word embeddings, how we calculate the attention. So we need three different matrices. So we need to run three different matrices: query matrix, key matrix, and value matrix. These three matrices are used to compute attention scores to improve the representations using this equation. So in this equation, the highlighted part is what calculates the attention scores, which are used to combine representations. That is attention between features, and this is how we output new representations. However, how can we use this for tabular data? This is where it comes that we change the input layer with the tabular data and create representation of tabular features, and everything else remains the same. And this is how we get the attention between features. However, as I mentioned, that tabular data has two different, it is heterogeneous features. So it has two different dimension, row and column, clinical variables and samples. So this is between the variables. Now, how we can run attention between clinical samples. So let's take an example that we have three different samples. And in these three different samples, let's create feature embedding for all these samples. This is the feature embedding for all these samples. Now, if we can reshape these samples in a way so that each row now represents a sample, and once we have each row as a sample, we can run the attention between these samples using the attention module that we showed in our previous slide. So this is how we can run attention between clinical samples. Now let's see how we can use this for our missing value imputation problem. Let's take an example of input dataset X, and we pass this to our pipeline where we first generate missingness completely at random with the missingness generator. This module gets executed for every mini batch. So we get random missingness on the fly for every mini batch. And once we have the missingness, we pass it to a cut mix method, which was conceptualized from contrastive learning to initialize those missing values. And once we initialize those missing values, we pass it to an embedding layer, and we get the embedding representation of the features. Once we have that, again, we take mix-up method conceptualized from contrastive learning and get a noisy version of the embedding that we had, and then we pass it to our attention module. It can be between attention, it can be between attention or self-attention. And once we have that, we reconstruct those embeddings to get the reconstructed version of the input X data. And once we have that, we backpropagate based on the observed entries. And this is how we run it and train it for our input data. Following to that, let's see how we evaluated our model. We took 80% data for training and 20% data for testing. And we did this experiment in 5-fold cross-validation. split. So for each fold, we take the training data, we train the model. Once we train the model, we take the test data and test the model and report the NRMSS score. NRMSS score is basically the normalized root mean square error. So we first take root mean square error for each clinical variable, and we divide it by the mean of that variable. And once we have the normalized root mean square error for each variable, we calculate this across all the clinical variables and take the mean to get the final normalized root mean square error. And once we have this result for all different folds, we take the mean and standard deviation and report it. For our experiment, we use 5 publicly available tabular dataset initially to validate our method on tabular dataset. So these are the 5 different dataset that we took from OpenML. And once we validate our tabular data method on tabular data, we train our model on electronic health record data taken from MIMIC database, which we have 2 different datasets, sepsis and hypotension. And this is the result on 3 experimental scenario where we have 10% missingness, 30% missingness, 50% missingness, and we tested on those 5 publicly available OpenML dataset to again validate our method's performance. And we can see that our method outperforms all the other baselines in all possible scenarios. And also, it's also observable that when we have high percentage of missingness, as you said, the mice and mixed forest does not perform well in high performance, a high missing rate. But however, our model always performs better than those. And following to that, this is the result on electronic health record data, where we report that sepsis and hypertension dataset, between feature attention outperforms all the other methods in 30% missingness. And this is the result that shows the improvement of sepsis is 26% to 74% on between feature attention compared to all the other baselines. And for hypertension dataset, we got 30% to 85.77% improvement in compared to all the other baseline methods. So we can see that our proposed method showed drastic improvement based on both on traditional method and also between sample attention method. So therefore, to summarize, the proposed method leverages attention between patient and between clinical variables, and a novel attention-based method with data manipulation technique of contrastive learning has been proposed, and our method outperforms state-of-the-art statistical models in 15 out of 17 experimental scenarios. And proposed imputation method is robust in all dataset with high missingness. And our method improved on mice by 74.6% missingness in all experiments, and on mixed forest by 54.74% on all missingness scenarios for tabular data, those 5 tabular data that we use for validation. And for the ICHI data, we see that our method achieves 52.6% to 82.6% improvement compared to other baselines on all the data sets. Therefore, we believe that our method will reduce misdiagnosis due to missingness of clinical samples, will help keeping clinical variables with high missing rates instead of omitting the clinical variable that might carry high predictive coefficient values. And we can do better analysis of IHR data following data imputation. Therefore, to conclude, we can say that deep attention-based methods are poised to surpass traditional methods, and the proposed method outperforms other baselines in almost all scenarios. In the future, more work is needed to improve data imputation of tabular data. For example, higher rate of missing data can be considered. Other type of missing data can, for example, missing not at random, missing at random can be considered. And also, we are curating all of us research data to perform imputation on large-scale real-world IHR dataset. So thank you for listening to this presentation. This is the reference that we have used for this presentation. If you have any question, I'll take them now. Thank you.